All right, thanks everybody for coming. We're going to do Trevor Host's Master's Defense today. Trevor's from the Duluth area. He did his undergrad at Wisconsin in environmental science and then decided to come to the proper university and do his master's here, which is in NRSM. He's done a lot of work with point clouds, both LiDAR derived and photogrammetric point clouds. We're going to hear about some of that stuff today. Trevor's been fantastic in the lab. He's a really great guy, those of you that know him. Really hard worker, does a lot. Really happy to have him in the lab, and we're very happy also that he's going to be hanging around for a little while in a staff position working with Matt and me on two projects. So very exciting. I guess that's all I have to say. Trevor, take it away, man.
All right, thank you very much, Joe. The title of my talk is Measuring Mapping Urban Tree Canopy with Remotely Sensed Data. So I've worked in the remote sensing lab for about 2.5 years now. I started out working on a high-resolution land cover classification project that was in combination with the statewide classification. I was focusing more on the urban areas and then rolled that into an urban tree canopy assessment for Minneapolis and St. Paul. So in the remote sensing lab, we kind of have a different perspective on the landscape. So we're looking at things from the top down, from far away. We're using satellites, airplanes, and drones to monitor change over large areas on the landscape. So really looking at broad areas and then monitoring changes through time. You can see some of the changes here occurring. This is from 1980s to 2017. The airport develops over time. The wetlands change throughout the years. Roads develop. The urban area is really dynamic ecosystem. There's tree canopy as well as urban environment. So what I'm interested in doing is using remote sensing to quantify these changes and quantify the landscape using remotely sensed data. So specifically focusing on the tree canopy in the urban area. So why tree canopy? It's very important for many reasons. Well, big reason is cooling effects. Urban heat islands is a big problem. Tree canopy can provide some mitigation of that. There's stormwater management benefits to urban tree canopy. And there's things like wildlife habitat and many other benefits. And these all have economic value as well. So what I'm interested in doing is mapping where the tree canopy is, both the abundance and then how it's changing through time, and what impact that has on the economic value as well as the environmental value. So there's threats to urban tree canopy as well. There's things like wind events, tornadoes knocking down trees in the urban environment. There's pests and disease, and just other urban stress. So the urban environment constantly changing, redevelopment is really putting stress on the urban trees. And there's quite a bit of management as well. So planting, things are just changing quite a bit. There's also climatic change as well, putting stress on all of our forests, including the urban tree canopy. So a big one around here is emerald ash borer. You notice all these green tag trees are ash trees that will likely be gone in the next 10 years. I found that there's about 5% of the trees in Minneapolis are ash trees. And emerald ash borer has been here since about 2010. And you'll see where that kind of fits in with this analysis and why it might be time to update it with new data. So with remote sensing, there's two different forms: passive sensing, active sensing. Passive sensing be like imagery collected through either aerial or satellite forms. It's measuring the spectral response of the landscape. Alternatively, there's active sensing, which is something like LiDAR or radar. We use mostly LiDAR for this, which is sending a laser pulse down to the earth and recording the time that it takes for that pulse to come back and getting a detailed estimate of the landscape. So that there's LiDAR pulses that penetrate through the tree canopy to the ground, and you're really getting it produces a point cloud, which is a three-dimensional representation of the landscape. So what I'm interested in doing is taking both of these data sets and combining them for the most accurate analysis that we can achieve. So LiDAR data in the Twin Cities exists for everywhere in the state, but we're particularly benefited by the fact that there's high density LiDAR in Minneapolis and St. Paul. That orange box is 8 pulse per square meter LiDAR, which in the grand scheme of things, it's not super high, but it's more than elsewhere in the state, which is approximately 1.5 points per square meter. So this higher density LiDAR is, there can be more things extracted from the three-dimensional information. It was collected in the spring of 2011, classified by the American Society of Photogrammetric and Remote Sensing classification standards. So things like ground, buildings, vegetation, and then overlap between the flight lines are classified, the individual points themselves. There's also intensity of the return is recorded as well. So this high density area is where I chose to do the more detailed assessment of tree canopy. So this is what the point cloud looks like. This is a tree that's right out the window here. So this is the density of data that exists for that whole area covering Minneapolis and St. Paul. So things that I'm interested in pulling out are things like, well, basically the tree height, maximum height, crown area, be kind of the most general measurements. But then also things like crown height, distance from the top of the tree to the lowest branch, and then the lowest branch to the ground, be the trunk height. And then also volume. So volume means different things in terms of forestry. And what I'm kind of interested in here is the volume that the tree actually takes up. So if you were to wrap the whole tree in something like plastic, what would the volume be? And so we've thought about this quite a bit and in different ways that we can estimate three-dimensional characteristics from this LiDAR point cloud. And here this, because it's a vertical structure, has 13 points per cubic meter, which is kind of another way to think about it in a three-dimensional sense. So there's different ways that you can process the point cloud. The basic processing is interpolating a surface model from the points. So translating the points into a more normalized raster surface that can be then related to the imagery. There's different ways to create surface models. Traditionally, it's interpolating the first returns in the point cloud. But sometimes that can cause errors like these spikes that go to the ground. A first return that reaches the ground doesn't really represent the true tree canopy. Sometimes points are miscoded correctly, and we want to be able to use the data to its fullest extent. So using LAST tools, which is a LiDAR point cloud processing software, they came out with a new method that's called the spike-free algorithm. It creates a surface model from the maximum of the points in three-dimensional space. So it's using the X, Y, and also Z component to interpolate between points, producing a much more continuous model of the canopy, and is a little bit better for distinguishing between two tree objects. So here's another look at a point cloud. This is another tree that's right out in front of the gym, big bur oak tree that you might know well if you work here, or you probably walked in on your way in. So this is the density of the data. You can see branches within this tree, and it's really high quality stuff. Using the more traditional methods, though, you get this spiky model, which doesn't really represent the whole tree canopy itself. Using the spike-free method, we're able to create a much better surface model, modeling the tree crown itself. So that's pretty good for measuring things like height and crown area. But then we wanted to look further at the volume of the tree, because there's space below those lower branches that really isn't the tree canopy. We want a way to automate the extraction of those kind of metrics. This is what it looks like in surface model form. The top one, not super usable, and the bottom one is quite a bit better. So produce this surface model for that whole high point density area. So taking a look at this same tree again, in terms of three-dimensional space, we thought about this for quite a while, kind of came up with an idea to model the underside of the tree canopy as well. So the lowest hanging branches now create the surface model, and be able to calculate then the height of the crown. But that's kind of hard to do with the current software. But one of the ways you can trick it is to invert the tree crown, and now create a surface model of the top, which is now the bottom. The lowest hanging branches, create a surface model using the similar methods, spike-free algorithm, and then revert that so it's back facing upwards. And then now we have two surface models that represent the whole crown of the tree. So the maximum digital surface model, and then the minimum. And finding the difference between those surface models, calculate the height of the crown. So that looks pretty interesting. How does it work when you have multiple trees next to each other, though? So here's another example, right across the baseball field here. Here we have multiple trees, different heights, varying densities, and create a minimum surface model and a maximum, and put them together to calculate the crown height. And you notice that there's spikes where the tree trunk is, and it worked out pretty well in modeling the underside of the tree crowns here. And that was a pretty interesting result. So we created this as well for the whole high point density area. Another thing to think about is slope. So these point clouds were normalized to the ground. When you normalize a point cloud to the ground, especially on sloping terrain, the points of the branches that are hanging downslope are going to be normalized higher than the points of the trunk or the points that are upslope. So when that happens, you're creating systematic distortion in points that really isn't there and can influence the calculation of height and volume that you do subsequently on the point cloud. So this is in Minnehaha. You can see the difference between the unnormalized point cloud and the normalized point cloud, where lower hanging branches are being shifted upwards and the upslope branches are being shifted downwards, creating a distortion. By using the crown height model, calculating the underside of the canopy, you eliminate some of that slope distortion. Other method. This has been researched as well, and this consensus is generally to use the digital surface model unnormalized to calculate your tree heights, so that you're considering the whole tree crown as an object. So this is Minnehaha. The ground slope here is 32 degrees, probably some of the most steeply sloping terrain that we have around here. So that's kind of the most extreme example in our area of versions of the data. But the offset eliminated with objects. This is also done through a divide and conquer process. So it's an iterative process, works through the data, first segmenting out everything that's tall in the landscape from the LiDAR data, and then splitting those into either tree canopy or buildings based on their spectral response. Then we can further break down tree canopy into things like thickness and deciduous. So this kind of broad scope. Here's an example of here in the campus. This is the gym. Here's our building, Green Hall. So this is what the nape imagery looks like, 1 meter resolution. First step is to classify everything that's tall in the landscape. So everything there in orange is from the LiDAR data. Next up, we pull out the buildings. Things left over are tree canopy. So now we've classified buildings and tree canopy. There's still a bunch of pixels that are still unclassified. Bring in other ancillary layers such as roads. Perform more segmentation algorithms for impervious surfaces. And then finally, grass and shrub. And then finalize the classification and output it as a result. So that's just a quick rundown on how the classification process works. This is all done through eCognition software. So we produced this for the 7-county metro area, and as well as Duluth and Rochester at 1 meter resolution. This was using the 2015 NAPE imagery, 2016 Met Council leaf-off imagery, and the LiDAR from 2011. So we produced pretty high resolution, well, really high resolution, 11 classes, and you can see the difference in the landscapes here. So then you can do things like calculate the amount of area of tree canopy. So for example, Duluth, 22,000 acres, and it's about 40% of the land area in Duluth. We assessed the accuracy and found that for most areas it was around 90% accurate with completely just the automated approach. So it did the same thing back here in the Twin Cities, splitting by municipality and calculating the area, or percent area of urban tree canopy within each municipality, as well as potential for urban tree canopy, which is other vegetated surfaces that aren't tree canopy, could be converted. Trees could be planted as they grow, fill in the tree canopy. So as you might expect, the urban developed areas are lower than, and as you move outwards from the city center, urban tree canopy increases. But there's quite a bit of complexity within this area. So I want to talk a little bit now as to the next steps, is really thinking between what's the difference between classification and feature extraction. So some of the differences are that classification, you're assigning a value to every single pixel in the landscape, and it's raster based. So raster means that there's one value per pixel. Feature extraction, with this high resolution, they look really similar. But what the difference is these are now converted to vector format, and you can assign multiple attributes then to each object within the extracted class. And so that's really kind of what led me to the next step of this project, wanting to identify individual attributes for particular canopy objects, and being able to segment this further now that we have some features extracted. Can we get down to almost an individual canopy level and do this in an automated way for rapid tree inventory? So that was the next step. We take that extracted tree canopy from the classification and use another layer calculated from LiDAR, which is a slope layer. So that's essentially the variation within a window of pixels of height. So it really highlights the edges. You see the edges of the buildings and the edges of trees. So we include this layer into segmentation with multi-resolution segmentation, considering multiple raster layers, and producing segmentation objects for within the tree canopy class for individual tree canopy objects. A point layer was also produced. Vectors can be points, lines, polygons. You can produce polygons and points. And each one of these has now calculated the maximum height for each object, the area, as well as the volume from our crown height model. So here's how it looks. This is still right here on campus. And this is probably one of the better areas where it worked out. Highlighting the edges between tree canopy is the goal. But sometimes you're going to have cases where multiple trees are merged together into one object, or a single tree is merged or split into multiple objects. So those are the two errors that occur, and try to minimize them as much as possible, but it's an automated approach and unlikely to get all of them. Another thing to note too is that understory can cause big problems with this approach, because being pixel-based, we're losing information that's hidden by the tree canopy that overlaps another one. Highlighting those edges helps in identifying those differences, but it's not always perfect. The point layer turned out pretty good though. Points are coded as the maximum point for each tree crown. So here's that overlaid on some imagery as well, and it did pretty good in this area. So we produced this polygon layer for the whole high point density area. Found that there's 3.4 million individual objects, just under 600,000 in both Minneapolis and St. Paul. Calculating height, area, crown volume, and then also calculated the mean NDVI, which is a spectral response between the near infrared and red bands in the imagery. So these values are all at, there's an attribute for every single object with those attributes. So then we can summarize by communities. So these are the number of objects, average number of objects within each one of these communities. So essentially trees per acre. The downtown areas have the lowest, as you'd expect, and then along the river is the highest. And really starts to describe the complexity of tree canopy in the cities. So we had to do some validation on this as well, with some ground measurements as reference. So this data is from Eric North. He measured 481 trees for height, as well as crown area. Crown area was calculated by 4 radial measurements, and then projecting an ellipse for the crown area. It was measured with a hypsometer, and we found that there was a good correlation, but there was systematic underestimation by the LiDAR height-derived measurements. And so that could be due to things like the laser pulse missing the very top of the tree, or various other reasons. Found that there was about a 10% underestimation in the LiDAR heights relative to the reference ground measured heights. So that's something to think about. We then compared the crown projected area as well. And those ones really didn't work out so well. Underestimation again by quite a bit, but the error was very skewed. So some crown areas were much larger than we expected. So some of the reasons for that are that you're comparing LiDAR raster data with a projected ellipse for the crown. So just somewhat different ways to estimate the crown area. And there was some issue with the timing between the reference measurements. They were collected in around 2015, while the LiDAR was collected in 2011. So just some differences there. But really, I think this describes somewhat of the challenge of creating individual crown objects from raster data and relating it to measurements on the ground. But still pretty useful data. We can compare the histograms of each one of the cities in terms of tree heights. So the average tree in St. Paul is about 1 meter taller than the average tree in Minneapolis. And you can look at the histogram of all the trees. And so you can see that, hard to tell a little bit here, but there's somewhat more of the larger trees in St. Paul. And it could be due to having more shoreline with the Mississippi River. A lot of those trees are really tall compared to in Minneapolis. So then by summarizing all these attributes, you start to see a pretty detailed picture of the tree canopy in Minneapolis and St. Paul. So in terms of tree height and crown size, definitely darker areas being higher values. It looks like there's more abundance of tree canopy in terms of size in 3 dimensions, as well as a 3-dimensional increase in St. Paul versus Minneapolis. And we look at leaf-off and leaf-on NDVI as well, and the difference within each one of these maps, partially what you might expect, higher NDVI in St. Paul than Minneapolis in both dates, which I thought was pretty interesting. Some of these can be summarized tabularly as well, versus the total area. We're going to have lower objects per acre in both Minneapolis and St. Paul versus the broader area, which extends somewhat south from the cities. So then I also wanted to look at how the landscape's changing. We have the pleasure of having the 2009 urban tree canopy assessment as well, which is assessed with different data, LiDAR data from 2007, and then compare that with our 2015 version of the land cover. And what we found was that there's about a 3.5% of the landscape decrease in tree canopy and about an equivalent increase in paved surfaces. So what that means is not so much that we're paving more, but it's likely that the tree canopy is being removed and uncovering the pavement that's beneath. And that's pretty interesting. It corresponds with about 1,200 acres of land area in Minneapolis and St. Paul. And we notice that the other classes stay the same for the most part. So that was pretty interesting. But there are different classification methods. You want to investigate a little bit and see if the change that we're seeing is actually real change or just due to the methods of the classification. So this is remote sensing, so we can also map the data. So here's just pulling out the tree canopy in 2009 and in 2015. Pretty cool minimalistic map. You can start this up as positive values. We were able to eliminate those small changes by using the object-based approach, smoothing out those minor changes that occur on the edges of the tree canopy. So, yeah, there you go. So, wanted a way to deliver this data out to the user community, produce this into usable GIS layers for city managers or anybody that wants to use this data. So we published it to an ArcGIS Online web app. So that includes the tree polygon layer, which has attributes for each tree polygon. And then here colorized by height. So shorter trees by the road, larger trees kind of inset back behind houses. And then also in red here is the tree canopy loss. So canopy that's been lost since 2000, between the dates of 2007 and 2015. And then also the raster surface model is published as a tile layer. So let's see, I wanted to pull this up as well. I might have to slide it over. So we can start to explore this whole area that's been collected in terms of this surface model of change. So the pixel values in this represent in band 1 is 2007 normalized digital surface model, and in band 2 is the 2011 digital surface model. So everything that's red shows up as a loss between the two dates. Everything that's blue is a gain, so like the stadium wasn't there. And then everything in white is consistent. So there's where the New Bell Museum is. There were trees there at one point. And so you can start to see there's red spots all over this map. And remember that this LiDAR data is 2007 and 2011. 2011 was quite a while ago now, and just at the start of the Emerald Ash Borer. And I think what we'd see now, if we were to recollect this data, is a much greater change between the LiDAR data, at least. And that'd be really interesting to see for height calculations and monitoring this change. So turn this off for a second, and then just wanted to show the polygon layer as well. Here they start to come in. So we can click on each of these objects and then see the results of the attributes as well. So the area, the height maximum, leaf off and leaf on, NDVI, and then the volume calculated from the crown volume. And then also tree canopy loss, so the polygons that were derived from that LiDAR change data. So this was a pretty cool web map to put together, and I think it really describes the story of urban tree canopy change in Minneapolis and St. Paul using the remotely sensed data that we have. The real benefits to this is it's wall-to-wall coverage. You don't always know where the tornado is going to happen, so it's really good to have the baseline classification of tree canopy. And now we had it in 2007 for Minneapolis and St. Paul. Now we have it in high resolution for the 7-county metro area, and we'd like to continue expanding this way. So I'll reiterate those points. What we did today was automated extraction of tree canopy measurements from LiDAR data, so really thinking in 3 dimensions. And then also demonstrating the capabilities of having a time series of data to provide insight to the landscape change. With that, I'd like to say thanks to everybody in the lab and my advisory and community members, and just wanted to show this graphic. Just kind of demonstrates the kind of a lighter scanning illuminating the forest. I thought this was pretty cool. Found it just recently. It was actually collected with a drone shedding 1,000-watt light onto the forest. Anyway, thank you very much. Are there any questions?
I was curious with your observation that there appears to be decreasing tree canopy cover and increasing impervious surface, that was accounted for partially because of this overlap. Is there a way to address that by having separate layers or stacked layers, say to correct that impervious surface of roadways with the street maps so that that area stays constant for areas of known constant impervious surface, and then you don't have this anomaly of apparent offsetting changes?
Yeah, that's a really good point. And when we did the high resolution classification, we actually did produce 2 different maps. So one from a top-down approach where tree canopy is overhanging the roads, and then one from a bottom-up approach where impervious surfaces are mapped, cutting out the vegetation layer. So that exists for the data that is the most current, 2015. Did not exist for the previous date because we didn't have access to the full point cloud, various other reasons. But that definitely would be interesting to look at and quantify the amount of area of impervious surface that's actually gained as well versus what's just being uncovered.
An advantage of doing this kind of work in an urban area, in addition to the real value that you already talked about, is that there is generally wider spacing between trees, which makes it slightly easier to isolate individual crowns and so on. What are your thoughts about the where the technology is and the kinds of techniques that you've used here? To what degree are those would those be successful in a forest setting where spacing among trees, you know, looking at your canopy model, you have a more or less continuous canopy. Obviously, it would depend on the characteristics and attributes of the forest you're looking at, but how effectively would you expect it to be able to isolate individual trees and create useful data in that sense?
Yeah, but it does. It gets a lot tougher when you have a continuous forest, for sure, to be able to identify the individual crowns, because they really just blend together. So then you can start thinking about like what's going on under the story. So you saw that there was plenty of returns on the trunk of this tree as well.
Yeah.
And I think, you know, with this high point density LiDAR, you're getting some returns from the interior of the tree, and making use of those, I think, is kind of a key for identifying individuals within a dense forest like that. But it varies quite a bit. I mean, like conifers tend to cluster or separate themselves, isolate themselves somewhat, and you can do peak detection and things like that. Really looking at, I think, the variation in heights was super helpful for identifying the individuals within something that's continuous like that. But yeah, I mean, with an aspen stand or something where everything's growing together, it can be really tough to to isolate individuals. And a lot of times you'll have to use some alternative data to get at the density of stems and things like that.
So Trevor, just following up on that question, so if you get a chance with some of this to look at how species identification might work, supposedly lesser number of species in the city, maybe not, but can you speculate on species identification?
Yeah, so one of the things, I didn't try and do species identification with this work. And that's been one of the kind of the sticking point for remote sensing. It's tough to identify individual species. We're getting higher and higher resolution data. It still can be really difficult to pick out certain species because there's a lot of difference. A stressed tree that looks different than a healthy tree of the same species. So a lot of times those things can be pretty tough to do. One of the things I was really interested in recently was looking at time series of change, modeling the time series of spectral response of tree canopy. And I think that'd be a pretty useful way to identify individual species. And we know that hyperspectral data as well can be used for species identification, but it's very costly and tough to do. So it's still not quite out there and ready yet for automated species identification for remote sensing, but I definitely, that's kind of a keystone point that once we can do that, it would be super beneficial for a lot of forestry around. So.
I'm having trouble recalling what year you had that really big, it wasn't a tornado, but we just had those really strong winds that took out a lot of trees in Minneapolis. And did you compare your findings with like the city's tree inventory to see, I mean, is most of the decline that you're seeing from, sort of big storm events like that, do you think, or is there a way to say that?
Well, it's tough to talk about the cause of why a tree canopy has been lost. And, maybe it was an ash tree and they had to remove it, or perhaps it was a wind event. And I know there was a tree across the street from me that blew down in winds last year. So these things are happening constantly. Storms coming through and taking trees down. But and so you have to do a little bit of interpretation when you look at this data to say why something occurred. I do have the inventory for Minneapolis, and that was really interesting to look at as well. But I didn't do any comparison with other wind events besides that one that just really stood out, 2011.
Okay. So sorry guys, we have to move ahead. We're short on time in this room, so feel free to talk to Trevor independently, but we have to move on to the private questioning. Thanks for coming.